Okay, there are a lot of participants. We'll just wait for a minute before we get on to the session. I think few more are joining. Maybe we'll start in another 2-3 minutes. Okay.
Okay, ma'am.
Okay. So before we start, I think each one of you can just give a brief introduction of yourself, which university you're from, and which year of chemical engineering you're in. I hope all of you are from Beta Chemical Engineering only, because this is a core course of chemical engineering. So I hope most of you are from chemical engineering only. So I just need you can just give a brief introduction of yourself. Let's start with Rahil.
Good
I'm
evening. I'm Rahil from JNTU, Anantapur, with the BTech studying BTech third year in chemical engineering.
okay.
So I'm from Kadapa district, Andhra Pradesh only, ma'am.
Okay. Okay.
Um,
Yeah. Maybe next someone can just give a brief intro. You can just volunteer yourself.
Hi, ma'am. I'm Manoj Kumar from JNTU Anandpur.
Okay.
I'm studying third year BTech Chemical Engineering.
Okay. So who is next? Someone. Jnaneshwar.
Hi, ma'am.
Hi, Jnaneshwar.
I'm Dhaneshwar, studying third year BTech Chemical Engineering in JNTU College of Engineering, Anantapur, ma'am.
Okay. Okay. Good. Next. Roshni. Roshni, are you able to hear me?
Yes, ma'am.
Okay. So,
My name is Roshni Patil.
okay. Where are you from?
Ma'am, I'm from Bharati Vidyapit College of Engineering, Navi Mumbai,
Okay.
and I'm studying third year.
Okay. Okay. Welcome. Tiruvasagan.
Good evening, ma'am.
Good evening. Uh, so Tiruvasagan, in which college you are doing your, BTech?
Ma'am, I am from JNTU University, Anantapur, ma'am.
Okay.
Third year.
Okay. So Harsha.
Ma'am, good afternoon, ma'am.
Evening.
Sorry, ma'am. Good evening, ma'am. I'm Harshardhan, ma'am. I'm from JNT Chemical Engineering,
Okay.
third year.
Okay. Next. Teja.
Good afternoon, madam. I am Kodur Teja from JN to Anandpur, madam.
Okay. Okay. There are two Tejas, is it?
Kodur Teja, madam. I am
Okay. The other Teja, K Teja.
K Teja, Kodur Teja, madam.
Okay. 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 There is one more Teja also. Okay.
Sonti Teja, madam. Another Teja.
Okay. Sonti Teja. Okay. So Sonti Teja, you're also from same,
Yes, madam. Same college, madam.
Okay. 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 A quick round of others also, please just give a brief intro of yourself, just your name and which university and which year of chemical engineering you are in. Some more are there. Okay. So Mamta. So,
Yes, ma'am. Ma'am,
so
I am also JNT College of Engineering, ma'am.
okay. I think there are most of you are from JNTU, is it?
Yes, ma'am.
Okay. Okay. I think you all have a similar mail ID, some 20, starting with 20 and then some number, is it? I guess so. It seems your entry admit mail ID seems to be very similar. Okay. Okay. So someone else who wants to introduce yourself, please come up.
Hi ma'am, good evening ma'am.
Good
My
evening.
name is K. Rohit.
Okay,
I
welcome.
am third BTech Chemical Engineering at JNTU College of Engineering ma'am.
Okay, welcome. So anyone else who didn't give their introduction, or all of you gave? Okay, I guess most of you gave your introduction. So let me give mine as well. So okay, there is one more person, Renuka. Renuka, where are you from?
Good evening. Good evening, ma'am.
Good evening.
I'm Renuka, ma'am. I'm third year BTech Chemical Engineering from JNTU College, ma'am.
JNTU. Okay. So welcome. Anyone
Thank
else?
you.
Anyone else who is left? Nagaharini.
Good evening, ma'am. Myself, Harini. I'm from Anantapur, ma'am. JNTU
JNT.
Anantapur, studying BTech third year.
Okay. Okay, and then there's one more person, Sharan. Sharan.
Good evening, ma'am. I am from St. College of Engineering,
Okay.
Kottayam.
Okay. So you're from a different college. Meenakshi.
Yeah.
Yes, madam.
You're from JNTU, right?
Yes, madam. JNTU Anantapur, madam.
Okay. Fine. Yeah.
Thank you, ma'am.
Welcome. So, all of you have introduced yourself, I guess so, and nobody is left. Anyway, I'll just give my introduction as well. I'm Kritika. So, I'll be handling this live interactive session for you for this course Chemical Reaction Engineering 2. Okay, I am a PMRF scholar from IIT Madras. Okay, and a few points. So this session will be interactive. Okay, so you will be giving the answers. I mean, you will be stating, whatever you feel based on the question. Okay, and we'll solve it together. It will be more interactive. So, see, there is no right and wrong. Okay, end of the day, we have to learn. That's it. Okay, so don't shy away yourself. Okay, so feel free to ask questions and feel free to answer. Okay, and one more thing is that I request you to preferably go through the lectures, so that solving during this session will be much more uh, intense. Okay, instead of just I'm saying the steps, so you will be able to say the steps much more precisely. Okay, and also now your doubts will get clarified. Okay, this session is mainly intended for helping you solve your assignment questions, as well as to take up exams in a much better fashion, and also support you in learning. Okay, and also one thing is that if you go through the lectures, whatever doubts you have, you can ask during the live session. Okay, so whatever possible, I'll try to answer in the same session itself. If something I'm unable to answer in that session, I'll try to answer those in the following sessions. Also, I request you to post your questions in case you have in the forum, so that either I can reply, or else the course faculty or the other TAs, of this course will help you out in answering and clearing those doubts. Okay, so feel free to do those things. Okay, hope you all got my point. Yes, I need some reply.
Yes, madam.
Okay, fine. Okay, so hope you are all having some pen and paper with you. Pen and notebook, actually, it's not paper. I guess you're all having it. Yeah?
Yeah,
Yeah.
madam.
Yes, fine. Okay. So now let's go into the session. So you're all able to see my screen? Are you all able to hear me and see my screen?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Okay. Yeah. Okay. So I welcome you all to the course, interactive session for the course Chemical Reaction Engineering 2. The course instructor is Professor Ganesh Vishwanathan from IIT Bombay. Okay, and I'm Kritika. I'm a PMRF scholar at IIT Madras. Okay, so let's get into the session. So before actually going into the problem solving part, so every week we'll try to have a recap of the lectures of that particular week. Okay, there will be a brief recap of the lectures. This will be followed by a problem solving session, and then in problem solving session I'll try to solve some general problems, as well as I'll try to address some gate problems as well. So that will be very useful, I guess, for you all. And also I'll try to address whatever doubts you have asked through forums, uh, or during the live session itself. Whatever doubts you get, I'll try to address those doubts in the last part of the session. Okay, hope you all get my point.
Yes,
uh,
ma'am.
Yes,
yeah,
ma'am.
fine. I need someone to reply because I can't view when view if you're there or not, and if my connection is there or not when I'm actually presenting. Okay,
Okay, ma'am.
yeah, fine, thank you. Now let's get into the session. So did any of you go through the lectures? There can be yes or no as well.
Actually, we enrolled recently, ma'am. After this session, we will listen to lectures, ma'am.
Lectures, okay, but I request you, just before the live session, try to go through the lectures, and also please try to go through the lectures sincerely, because lot of efforts have been put by the professor. Okay, if you go through the lectures, you will really feel the depth and beauty of the subject, and you'll get a lot of you know perspectives and knowledge. Okay, so please go through the lectures.
Okay, ma'am.
Okay, yeah, so let's get into the session. So the first week had 5 lectures basically. The first lecture was a brief introduction to the course as such. Okay, where there was a discussion on what was handled in CRE one. For example, in CRE one, you would have gone through the kinetics, rate constant, order of reaction like first order, second order, zero order reaction, and all. And then you would have been introduced to a batch reactor, and then ideal flow reactor designs like PFR and CSTR, right? And then isothermal, and then adiabatic condition, non-isothermal conditions. I think these would have been covered in CRE1, right? Hello, are you all
Yes,
there?
madam.
Yeah. Okay. So in CRE2, so what were the what are the lecture contents? Those were given a brief, like this course will cover lecture contents like your catalysis and catalytic reactors, catalyst deactivation, and then the diffusion effects, and then fluid solid non catalytic reactions, and then the residence time distribution and all. Okay, so these will be the overall course content which was all discussed in the, and how many lectures for each of the content were all discussed in the introduction uh, lecture. Okay, and then a brief introduction on catalysis and catalytic reactors was given. Okay, where uh, the history of the catalytic reaction, right from when it was officially you could see some industrial process with catalysis that is happening and all were given, and what is the economic role of catalytic reaction. Okay, so that was all discussed. So these things really give a depth of why are we really getting into a catalytic reaction. Okay, say for example, this catalytic process, it's been like over 2000 years. Can you just give me some household process where a catalyst is involved?
I mean, cooking we add salt.
Is it catalyst?
Yeah, ma'am. It works as a catalyst, ma'am.
Is it so?
Yeah, ma'am.
I really doubt, because that is also not much of a reaction. A typical example you could say like making of curd, correct?
Fermentation, like that, ma'am.
Right. A typical example like making of curd or cheese, right? You will add some,
Yeah,
uh,
bread preparation,
yes,
cake, baking cake, like
yeah,
that.
yes. So these are all some classic household examples, okay, which are very close. So that means that there are a lot of catalytic reaction even in our very close vicinity, correct? So
Yes, ma'am.
it's really important, and uh, to understand what is really happening in these reactions and all, right? Yeah. And then in lecture 2, again, what is the definition of catalyst was explained, and then classification of catalytic reactions like homogeneous catalytic reaction, heterogeneous catalytic reaction. Okay, uh, say for example, can you cite any example of a heterogeneous catalytic reaction?
Ma'am, ammonia production.
Yes, yes. What kind of catalyst?
Iron catalyst.
Yeah, yeah. Okay. How do you say it is heterogeneous catalyst? Catalysis, I mean
Because,
catalytic reaction.
because ma'am, catalyst is in form solid form, and our hydrogen and nitrogen are in gaseous form.
Yes, yes. So that is a classic example of a heterogeneous catalytic reaction. I hope others also get to know, right? You're able to understand?
Yes, ma'am.
Yeah.
Yes,
I
ma'am.
think most of you would have, come across what is a catalyst, what is a kind of catalytic reactions and all, right? Some basics, at least in your, even in your 11th and 12th, you would have come across these terms, correct?
Yes, ma'am.
Yeah. Okay. So, and then lecture 3 was on catalyst properties and classification. Say, for example, catalyst properties. One of the key properties is the surface area. Okay, they provide a very large surface area. Say, for example, the surface area provided by a silica alumina catalyst is 300 meter square per gram. So per gram of catalyst give a surface area of 300 meter square. So that gives a lot of scope for kind of a reaction to take place, right? Right?
Yes, ma'am.
Yeah. So the catalyst, they tend to have pores, and they are called as porous catalyst. Okay, and some examples of catalyst systems and all were discussed, like silica alumina, Raney nickel, platinum on alumina, promoted iron, and then molecular sieves. What is the beauty of these molecular sieves is that the pores are of very small size. Okay, that they can be very, very selective to the reactant species. Okay, hello.
Okay, ma'am.
Yeah. And then the concept of supported and unsupported catalyst was discussed. Say, for example, you could have platinum impregnated on alumina. So that in that case, it is a supported catalyst. Okay. Whereas when you have a kind of a platinum gas, for example, that which is used in ammonia oxidation, so that is an example of an unsupported catalyst. Okay. And one of the key criteria of unsupported catalyst is that they are desired for a low pressure drop process, and where heat removal is an issue. Whereas when it comes to a supported catalyst, what happens is that there is a high pressure drop. Okay. And then the next topic was what was discussed was on how does a catalyst work. So basically, the reactants gets adsorbed on the catalyst surface. This is how a catalyst works. Okay, this adsorption can be a chemisorption or a physisorption. Okay, and then one of the key aspect is that catalyst, it just you know uh, 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 it as you all know that catalyst does not really get consumed during the reaction, right? It just supports the reaction. Hello, are you all there?
Yes, ma'am.
Yeah.
Yes, ma'am.
Yes, ma'am.
So what it tends to do in a reaction, does anyone know?
It increases the rate of the reaction, ma'am.
It
Increase the rate of
rate of
reaction, ma'am.
reaction, how does it do?
By decreasing activation energy, ma'am.
Yes, so it decreases the activation energy. So so does it really affect equilibrium of a reaction?
No, ma'am.
How do you say that? We could say that because it does not change the enthalpy of a reaction. Delta H of reaction doesn't change. That is, the energy levels of the reactants and the products are not affected by a catalyst. Whereas they just play a role in reducing the activation energy, that is, in crossing the energy barrier, okay, of reactant to get converted to a product. That is why it does not change equilibrium, whereas it only affects the rate. Okay, and then
Okay.
okay, Uh, and then there was a discussion on active sites. Okay, where actually your reactant gets absorbed, and then there was a discussion on classification of catalyst, based on the reactions. So what are the kind of catalyst, for different reactions? See, there are for example, in case of an alkylation and dealkylation process, there are set of catalysts like aluminum chloride and then palladium zeolites that are used. Whereas for your oxidation, you have your copper, silver, and then nickel, vanadium pentoxide. So these are some of the typical catalysts used. So, uh, those insights were given in the lecture 3. Okay, and then the lecture 4 was on steps in catalysis. So the catalysis process involves 7 steps. Does anyone have any idea on the 7 steps of catalysis? A catalytic reaction?
No, ma'am.
Okay. So the 7 steps are, so there is a reactant. Okay, there are reactants. Okay, they will be in bulk. Correct. So and you have a reactor with packed with catalyst. Correct. So this reactant has to enter into the catalyst, right? First they have to enter into the catalyst surface and then into the active sites. So you have from a bulk phase to the catalyst surface, it is the, what is it, bulk diffusion, okay, and or external diffusion. And then into the active site, it is the internal diffusion. And then when it reaches the active site, it gets adsorbed. That is the step 3. Okay, and once it gets adsorbed, so the reaction has to take place. So the reaction is the 4th step. And once the reaction happens, now the products are in the adsorbed state. Okay, so that is, so they have to get desorbed. So desorption is the 5th step. And then that product has to pass through the pores to reach the surface of the catalyst. So that is the again internal diffusion of the product. And then finally the product has to diffuse to the bulk. So that is the external diffusion of product. So that is the step 7. So these are the 7 steps. So you have 2 external diffusions, 2 internal diffusions, 1 adsorption, and then reaction and desorption. So these are the 7 steps. Hope you are you all there?
Yes,
Yes,
ma'am.
ma'am.
So these were all explained in detail in the lecture 4. And also a brief rate equation for external diffusion control and for internal diffusion control was derived. It was not derived but just explained. Okay. Okay. Now uh, let me ask you a question. In case of an internal diffusion, okay, the reactant has to pass through the pore, okay, of a catalyst, okay, and the catalyst will have a certain structure, like it can be a spherical or it can be cylindrical, okay, so that will have a particular diameter and dimension. Okay, so if the diameter of this catalyst is larger, then in what way does it affect the rate of reaction? So will it support positively or will it support negatively? Just have you gone through this mass transfer classes? Hello.
Yes, ma'am.
So any idea on the diameter? How does it affect?
मैम डायमीटर अगर कैटलिस्ट का ज्यादा होगा तो वॉइड्स भी उतने फॉर्म होंगे ना.
Yeah, you're trying to say that it will have more voids. I mean, more pores.
Yes, ma'am. Yes, ma'am.
No, I'm saying
Voids.
of the you know, uh, say for example, the pore diameter also. What happens if it is large?
Yes, yes, ma'am.
So what happens? So does it say does it affect positively or negatively diameter of the particle?
Po- पोर डायमीटर्स इंक्रीज होगा तो मैम उतने एक्टिव साइट्स भी बढ़ जाएंगे ना.
You will have, yeah, more active sites. But what about the diffusion effect? So what happens is that as the diameter of the particle, it is very large. Then what happens is that, or the depth is very large. Most of the reaction happens in it takes a longer time for the particle to reach the active site, actual active site. The so most of the reaction, what will happen is that it will take place in the surface of the catalyst itself. It will not get
Catalyst,
into the
catalyst.
active site. So most of your your catalyst gets wasted actually. So that is one point of view. And also, as the diameter of the particle increases, the rate gets, since it is more and more of your internal diffusion control, your rate decreases. In fact, the rate has a inverse proportionality with that of the diameter. Okay. Hope you got the point.
Yes, ma'am.
Yeah. When
Yes,
you go
ma'am.
through the lecture, you will get, much more better perspective with the figures and all. Okay.
Okay, ma'am.
Yeah. Now, and then the lecture 5 was on adsorption. So adsorption is the third step, right? I just
Yes, ma'am.
discussed the 7 steps of catalysis, right? So adsorption is the third step. So, uh, introduction on the adsorption process, and then adsorption isotherms, and then different types of adsorption like non-dissociated adsorption and dissociated adsorption was discussed, and then Langmuir adsorption isotherm was discussed. So, what do you think of this non-dissociated and dissociated adsorption? What happens in each case? Can you just give a guess? You need not be right. You can just give a guess. What do you understand by this term non-dissociated or molecular adsorption, sorry, and dissociated adsorption? What actually happens? Are you all there? You need not be right. You can just give a guess. What do you actually, understand by this term dissociated and non-dissociated adsorption? You can just give a guess. I'll give you the right answer. You don't want to take a guess, is it? Okay, let me say. See, for example, you have a carbon monoxide molecule. Okay, and then there is a it is exposed to catalyst. So, in case of a non-dissociated or a molecular adsorption, what happens is that this carbon monoxide as a whole molecule will get adsorbed onto one active site. Okay, whereas when it is a dissociated adsorption, what happens is that the carbon of carbon monoxide will get adsorbed to one active site, while the oxygen gets adsorbed to another active site. Okay, that is what is called as a dissociated adsorption. Okay, hope you are all clear. Hello, can I have
Yes,
some?
ma'am.
Yeah.
Yes, ma'am.
Okay. Yeah. Okay, and then we'll also have a brief recap of lectures of week 2 as well, because I think your assignment deadline is on 8th of February. So by the time we have the second interactive session, your assignment deadline for week 2 will also be over. So I'm just giving a brief recap also, okay, of week 2 lectures as well. Okay, in the week 2 there were again 5 lectures, and the first lecture of week 2, that is in overall it is lecture 6, was on surface reaction. So surface reaction is the fourth step in a catalysis process, right? So what are the surface reaction terms? So three different types of surface reaction. One was a single site reaction, and then a dual site reaction, and then Illy Riedel mechanism was discussed. And then what is the rate equation for a single site mechanism, and then what is the rate equation for a dual site mechanism. Again, in dual site you have three different. So this dual site mechanism is also called as Langmuir-Hinshelwood kinetics. Okay, and it involves three different mechanism further. So one is one adsorbed species, and the second one is two adsorbed species, and the third one is dual catalyst, that is dual catalyst with two adsorbed species. Okay, these are the three different mechanism within the dual site mechanism. Okay, and then there's a Eley-Riedel mechanism was discussed, again the rate equation, and then there was discussion on the desorption step. The lecture 7 was on rate controlling steps and rate law. So as we discussed and as it is discussed in the lectures as well, so there are 7 different steps in a catalytic process, right from external diffusion to internal diffusion to adsorption to reaction, desorption, and then again an internal diffusion of products to the surface, and then products from the surface to the bulk. That is again one more external diffusion. So among these 7 steps, any of them can be rate limiting. So what do you understand by the term rate limiting? Rate limiting step. What do you, or a rate controlling step? What does that mean to you? What do you think about the term? What does it mean, rate limiting? You need not say in the reaction term also. In general also, what do you feel by the term rate limiting?
Ma'am, actually, I guess
Ma'am,
if we want to decide a product, so if we want to limit the undesired product, so I think so.
Okay, you're saying that you know excluding the undesired product, so limiting its formation is rate limiting. Okay, so
Yes, ma'am.
okay, just hold on. Let's see what Roshni says, or what Roshni thinks about it. She was also trying to say something.
it is uh, slowest step rate determined.
Yes, yes. So, Mamta, what Roshni said is correct. Here it is actually, the slowest step, or that is what is controlling the whole reaction. For example, let's take a typical, uh, say for example, some running race also, right? So, we have some 4 or 5 people. One person completes in 5 minutes, whereas another person takes 10 minutes, and the third person takes 20 minutes. Okay, now they say, what was the overall rate of this running race competition. Okay, then it will be, or what is the time span, or of this entire running race event. Then it becomes, you cannot say that the entire time span of the running race event was 5 minutes, because the first person completed in 5 minutes, right? It is decided by the third person who completed in the finally, like in 20th minute. So the overall time of that event was 20 minutes. So the third person is the rate controlling factor of that whole event. So it is the same in the reaction also. So it is the slowest step that controls, you know the entire reaction. So some, for example, in these 7 steps itself, some your bulk diffusion might be, taking place in fraction of seconds. Your adsorbent might get absorbed, like, so once it sees the catalyst site itself, it gets absorbed. But the reaction, it may take time, or else sometimes, the material to pass through the pores might take a longer time, or else the time taken for it to get absorbed. So once it enters the catalyst surface, it has to get absorbed. So that, there might be some competition between molecules to get it absorbed and all. So that kind, take a longer time. So these are, basically your rate limiting or rate controlling step. Whatever you were saying, Mamta, it is more of selectivity. Okay, when you
Okay,
have a
ma'am.
better selectivity, then you can limit your unwanted products or undesired products. Again, catalytic reaction is more on selectivity also. So to avoid undesired products and all, you again go for a catalytic reaction. That is what I told when when I was saying on this molecular sieves, right? They can have very good selectivity, because they'll allow only very small molecules. So only that small molecules can pass through, and the reaction can take place. Okay. Uh, so that was about the rate limiting step. So and then what are the rate limiting steps in some classic reactions was discussed. Say for example, in case of ammonia synthesis, you have your nitrogen and hydrogen, right, which reacts to form ammonia. So the adsorption of nitrogen is what takes, a lot of time, or it is what is the rate limiting in case of ammonia synthesis. Whereas when your carbon monoxide and nitrous oxide reacts, CO and NO reacts, the surface reaction is the rate limiting. So it changes from reaction to reaction also. And even when we change the catalyst also, no, the rate limiting step might be changing. Okay, because the affinity to particular catalyst, that will also decide the rate limiting step. Okay, and then, so what are the major steps involved in deciding a rate law? Because you have 7 different steps of a catalytic reaction. So what is the possible mechanism? See for example, all the reactants may not get adsorbed to the uh, catalyst surface. Some might get adsorbed, some might react through the bulk itself. Okay, and some, as I said, in a dissociated manner, they get absorbed. So what is the mechanism? We have to postulate it, and then we have to decide on the rate controlling steps. We have to find the rate law, and then validate with the experimental data. So if the experimental data and whatever we have found out, formulated the rate law, if it matches, then that is the rate law with that particular rate controlling mechanism. Otherwise, we have to again go back to the step 1, and we have to postulate a different mechanism. So those were discussed in lecture 7, with an example of cumene to benzene and propylene conversion. Okay, here there was an assumption of a dual site mechanism of Langmuir, LH mechanism, and then where adsorption as rate limiting, when, for example, in case 1, adsorption as a rate limiting step was discussed, case 2, surface reaction as rate limiting, and case 3, desorption as rate limiting, and how did the rate law look like in each of these cases was all discussed in lecture 7. And then lecture 8 was on rate law with a pseudo steady state hypothesis. Okay, so in the previous lectures and all these mechanisms, whether it is adsorption or surface reaction or desorption, it was all discussed based on all the reactions were reversible. But there may be in actual scenario cases where there will be in some part of the process some irreversibility. So what if any of these process, one or more of these processes are irreversible? So that was discussed in uh, lecture 8, where a balance or rate of generation of the intermediate species, once it gets absorbed, so a kind of intermediate species is formed. So that rate is assumed as a pseudo steady state. That means consider that as a pseudo steady state, equating the concentration of these intermediate species to 0, and proceed with the rate law formulation. Okay, here an example of isomerization of N-pentene with surface reaction as a irreversible process was discussed, and which was also considered rate controlling. Okay, then a brief on temperature dependence was discussed. Obviously temperature will have a role, right? Are you all there? Will temperature have a role or
Yes,
not?
yes, ma'am.
Definitely it will have a role, right? Because even your the rate constant term is a temperature dependent, right? It is a Arrhenius
Yes, ma'am.
rate dependent. Yes, and similarly your adsorption and desorption processes are also temperature dependent. Only thing is that these things should all be in a single kind of it should come to a kind of a everything should match in terms of temperature. That is your adsorption, your reaction, everything should be favored in kind of a single or a particular range of temperature. If it gets absorbed in some temperature, whereas there is a huge difference, then the probability of the catalytic process supporting the reaction might not be proper, right? So the catalyst should be functional, it should be able to absorb the species at the reaction temperature. So that becomes very critical aspect of a catalytic process. Okay, and then the lecture 9 was on heterogeneous data analysis for reactor design. So what are the steps involved in designing a reactor for a catalytic process? So first we have to deduce a rate law, and then find what is the mechanism. So which one is rate controlling step? Okay, which are the steps that takes place rapidly? So those are to be determined. And then once you formulate the rate law, then we have to find the rate parameters. So what are the rate parameters? You will be having your rate constant, different rate constants, some depending on the adsorption and desorption, and some of the surface mechanisms, so combination of these. So these rate parameters are to be determined, and then you have to go for a design of a reactor. So for this case, an example of demethylation of toluene was discussed. Here, a rate law was deduced from the experimental data, uh, where the role of different reactants and products on the rate, uh, information or experimental data was given, from which a particular mechanism was assumed, and then the rate law was formulated, and the rate expression for adsorption, surface reaction, and desorption was all written. Okay, and the final lecture was again a continuation on this heterogeneous data analysis for the reactor, where the rate expression with surface reaction. So from the mechanism and from the experimental data, it was assumed that surface reaction was a rate limiting step, and then a rate expression was derived. And then one particular case where we neglect the reverse reaction was formulated, and then the rate parameters were deduced. So how do you deduce the rate parameters? Is through the mathematical techniques. Okay, through regression analysis you will tend to deduce the rate parameters. So after deducing the rate parameters, so what is the uh, you know ratio of this toluene to benzene? Okay, what should be the ratio of the adsorbed toluene to adsorbed benzene should be there for a particular conversion? Say in this case, it was discussed on 25% conversion. Okay, so what should be the ratio? That was discussed. Then design of a reactor, packed bed reactor, was initiated, where the performance equation was derived, and then the terms were plugged in for the overall reaction rate from the rate law. Okay, so these were all the contents of week 1 and week 2 lectures. So if you go through the lectures, you will get better insights on the entire content. Okay, so now let's get into the problem solving. Hope you're all clear. At least you got some brief insights, right? Hello? Someone can respond.
Yes, ma'am.
Yeah, okay, okay. Okay, now let's get into the practice assignment. So, one parameter that quantifies activity of a catalyst is any clue? I I doubt you might have an idea. Did any one of you go through the lectures? Then you will have an idea. Otherwise, I feel it might be very difficult. So, shall I say the answer? Shall I say? At least some response, please.
Yes, ma'am.
Yeah. Okay, I'll say the answers. I think most of you didn't go through the lectures. So it is actually the turnover frequency. And what is turnover frequency? Is the number of molecules reacting per active sites per second at the condition of the experiment. Okay. So as more and more molecules are reacting per active sites per second, then the activity of catalyst is much more, right? Right, are you able to get some idea? Hello? Okay, anyway, let me go on to the next question. The mechanism where reaction is between an adsorbed molecule and a molecule in gas phase. So I discussed like there might be different mechanisms, like all the reactants might get adsorbed on the catalyst surface, or there may be some cases where one or more of the reactants gets adsorbed, whereas the other reactants might directly react in the gas phase or the fluid phase, whatever it is. So what is this mechanism called? It is actually the Elie Riddle mechanism. Okay, this is how it happens. So are you able to see the pointer? Hello?
Yes, ma'am.
Yeah. So so these kind of triangles you can think as the active site of the catalyst. Okay, and one of the reactants here, it is a benzene, right? So this benzene is adsorbed onto the catalyst, right? Whereas your propene, it is still in the gas phase and it reacts with the benzene, okay, to form uh, the product. So this is what happens in case of a Illy-Riddle mechanism. Okay. Now let's go on to the question number 3. So are you all able to follow and get some insights?
Yes,
Hello?
ma'am.
Okay. Yes, I heard some S. Okay. Now let's go on to the question number 3. Tertiary butyl alcohol is an important octane enhancer that is used to replace lead additives in gasoline. Okay. So tertiary butyl alcohol was produced by liquid phase hydration of isobutene over an amberlist 15 catalyst. The system is normally a multi-phase mixture of hydrocarbon, water and solid catalysts. However, the use of co-solvents or excess TBA can achieve reasonable miscibility. The reaction mechanism is believed to be as follows. Okay, what happens in this case is that here I have denoted isobutene as I, water as W, and tertiary butyl alcohol as TBA. Okay, you are able to get it right. Okay, so what happens is that this isobutene will go and get adsorbed to a and S denotes the catalyst site. Okay, and here there is only a single catalyst, that is amberlist 15, which is denoted by S. Okay, so this isobutene gets adsorbed to catalyst site and form some intermediate IS with the catalyst site. So how you can imagine is that this formation, for example, is one second. Sorry, one second. Yeah, this formation, as you saw, is denoted by this I dot S. Okay, you're able to follow. Hello. I just request someone to reply yes or no, because I can't see when you're not there. I mean, when I'm in presentation mode, I'm sorry. Okay. So similarly, water also gets adsorbed to the catalyst side and form, the adsorbed system is W dot S. It is denoted by W dot S. And both these adsorptions are a reversible process. And once both gets adsorbed, this water on the active side plus the isobutene on the active side reacts to form tertiary butyl alcohol, which is again in an adsorbed fashion with the active side, and there one more free active site is obtained the end of the process. Okay, because there are two active sites that are there, and since there is a single product, one more free active site will come into the picture. And then this tertiary butyl alcohol, what it does is that it again gets desorbed from the active site. Okay, uh, as according to this mechanism. So all these steps are all reversible mechanisms. Okay, now we have to derive the rate law, assuming surface reaction is rate controlling in case 1, and in the second case adsorption of isobutene is rate limiting. So how do we derive this rate law? One second. So what are all given I explained the reaction mechanism, right? Now, this reaction is a dual site two adsorbed species mechanism. Why do you think it is dual site two adsorbed species mechanism? Hello? Hello, are you all there? Someone can reply.
Yes, ma'am.
Yeah. Why do you think
Yes, yes.
it is a dual site two adsorbed species mechanism?
Ma'am, because what is absorbing to side, active side, and it's isobutene also.
Yes. So there are two reactants and they are getting adsorbed to two active sites. That is why it is dual site two adsorbed species. Okay. Now we have to start forming the rate equation. So for the first reaction, so isobutene with getting adsorbed to the active site and forming I dot S. So what will be the rate law for this step? So it will be like this. So here I am denoting it for adsorption. I is for your isobutene. Okay. And Ki is the forward reaction adsorption rate constant. And so what will happen in general? You will have K1 into concentration of I into concentration of vacant site, right? For the forward reaction. Minus for the reverse reaction, you will have K minus 1. Sorry, K minus I. Where K minus I, you denote it for the desorption or the reverse reaction, right? Into concentration of that, isobutene active site complex, right? CIS, right? And then what you do is that you just take out K1 as common. So what will happen? You will have K minus 1 by K1 in the second term. That is nothing but your equilibrium constant, inverse of equilibrium constant of isobutene, right? That is why I have mentioned it as CIS divided by capital K1. You are able to get that, right?
Yeah, ma'am. Ma'am, what is CV, ma'am?
Huh?
What is CV, ma'am?
Yeah, CV is the concentration of the vacant site. So S denotes the active site, right? So this active site, which is a free active site, we denote it by, or vacant active site, we denote it by V. CV. Concentration of that we denote it by CV. Okay? You get,
Okay, ma'am.
yeah, fine. So this is for the first reaction. So can you say for what will be for the second reaction? Can someone say what will be for the second reaction? Does it look very similar to the first reaction or first step? First
Yeah,
step.
ma'am.
So what will be the rate expression?
RBI equal to K1 of K1 or K dash 1 of CW CV minus CWS by capital K1.
Yeah. Yes. So here, as you said, it will be very similar to the first expression, first adsorption expression of isobutene. Here it is nothing but your species is changed to is different water. So where you denote whatever you have denoted for uh, isobutene as I, here for water it is denoted by W, right? So you get a rate of adsorption of water is Kw into Cw into Cv minus of C concentration of Ws by equilibrium constant of water, right? Are you all able to follow? Hello?
Yes, ma'am.
Yeah. Okay.
Yes, ma'am.
Yeah. Now what about the third step, the reaction step, where water in the active site and isobutene in the active site gets converted to tertiary butyl alcohol adsorbed in the active site plus one more free active site. What will be the expression for this? It is a reversible reaction. You would have come across reversible reaction in your CRE1, right? So, and from the first two expression, you will get an idea on what are the terms, concentration terms to be there also. So, what will be the expression? Don't worry about these, suffixes and all. Just say what will be the expression. You want to give a try or shall I say? You can just say whatever you think might be possible.
K, K1WS CIS minus K2 TBAS. Yes, ma'am.
Will it be only CIS or water term will also be there?
Yeah, ma'am. CWS. CWS CIS minus K2 TBAS. Yes, ma'am.
Yeah, yeah. So as you said, there will be four terms. So again, the rate expression is very similar. Only thing is that this is for the reaction. So you have some reaction rate constant of the forward reaction. So the multiplied by the concentration of your water that is adsorbed and concentration of isobutene that is absorbed minus concentration of TBA that is that is in the adsorbed state multiplied by the one more active site, free active site what we get in the during the process of reaction, right? And divided by the constant, right? Since we just bring this Ks forward reaction constant outside, so you will have this constant in the denominator because inside it will be like K minus S by Ks, which is nothing but you can take it as capital Ks. Okay, and then your desorption step, which will be very similar again. Your RD will be Kd into concentration of this complex minus uh, concentration of TBA plus concentration of this and multiplied by concentration of this vacant site that is being formed divided by your desorption equilibrium constant. Okay, now sorry yeah. So now we have the surface reaction is rate controlling. When surface reaction is rate controlling, then your adsorption and desorption process must be very rapid, right? Because surface reaction is the slowest step, correct? Hello, right? Are you all there? Okay. Anyways, I'm just continuing. So your desorption and adsorption are in equilibrium. So their rates are zero. So this is what you get. So when the rates are zero, so you will equate rate expression for adsorption of isobutene to zero, and then you will find out CIS. What is the expression for CIS? Why should we find what is the expression for CIS? What is the necessity that we have to find an expression for CIS? Any clue? Can we experimentally
Ma'am,
determine what is the...
it is intermediate.
Yes, it is the intermediate, and it cannot be experimentally determined, because you can determine what is the concentration of the reactants and concentration of products, right, during the experiment as the experiment progresses. But you can't find out the intermediates, because it gets formed and it gets consumed as well. So it's difficult to quantify your intermediates. So that is why you have to convert whatever unknown terms are in this expression. For example, in all these expressions, like your C, concentration of is, concentration of ws, concentration of tbas, right, all these terms you have to uh, find out, right? Sorry, I'm having some issue. Yeah. So similarly, as I said, both the adsorption steps are rapid. So again here, the adsorption step of water, the rate of that should also be equated to 0. So you will end up with one more expression for concentration of ws, right? And then similarly, you will be ending up with an expression for the desorption step also, as that is also the at equilibrium. Okay, and the rate is 0. So with these things, there is one more thing that cannot be determined experimentally. What is that? Or it might be hard to determine. What is that? You're able to guess anything? Just see into these expressions. You can experimentally determine CI based on your input. CW you can determine. CTBA you can determine, right? These are all again rate parameters, equilibrium constants, which you can based on thermodynamics and other things, you can databases, you can determine those things. What is one more thing that cannot be determined easily by experiments? When the reaction is happening, or when the process is going on. The other thing is the concentration of the vacant site. You can get to know what is the total sites available, active sites available, but it's hard to determine what is the vacant site. So you have to use a mass balance equation for that. So total sites or total active sites on the catalyst is equal to vacant sites plus the adsorbed sites. So in this case, the adsorbed sites can be either your reactant adsorbed sites or product adsorbed sites. So the summation of that will give the total sites. So this total sites can be determined. So from this, you find out what will be the concentration of the vacant site. So you plug in all the other terms, okay, into that and find an expression for that, right? Now we know that the reaction is the rate controlling. So we write the expression for the reaction. Now what should we do to find the final rate law? So what are we supposed to do is that, what are we doing is that we'll just plug in the expressions for all the intermediates and whatever that cannot be determined, like for example your vacant site concentration, your intermediates like your adsorbed tba, your adsorbed isobutene, your adsorbed water, everything you just plug in those terms, and then you find the total, no what is the rate law. Okay, sorry. So this is the total rate law, right? Are you all able to get it?
Yes, ma'am.
Okay. Now, let's go to another scenario. Where adsorption of isobutene is rate limiting. So, when adsorption of isobutene is rate limiting, so what are the steps that are that takes place at a rapid pace? Can you just say? We had 4 steps, correct? So in which I'm saying earlier we solved a case where reaction is rate limiting, right? Now I'm saying adsorption of isobutene is the rate limiting. So what are the other steps that are not rate limiting? What were the steps for the reaction? Do you remember? I just request you to interact. Otherwise, uh, it will be kind of monotonous that I only speak. Right? It's nothing right and wrong. You can just say whatever you saw. It was already there in the question, right? What are the steps? So these were the steps, right? So now I am saying adsorption of isobutene is rate limiting. So which are the other steps that are very fast? You can just see the expression and say, right? So since adsorption is rate limiting, you want to make a try? Someone?
Yeah, I mean, absorption of water will be more onto the vacant site and tertiary bit or less state. Absorption will be more on site.
Yes. Desorption of TBA will be faster step and also your reaction is going to be faster step. So all these are going to be in equilibrium. That means all these rates you will be equating it to 0, right? One second. So that is what I have mentioned. So adsorption of water, surface reaction and desorption of TBA are all in equilibrium and their rate are 0. Okay. So again what you do is that you find out from each of these cases when you equate it to 0, what is the expression for concentration of the intermediate. Here you can get CWS, and then from the second expression for the reaction you can get what is CIS. But still in the CIS term you have CTBAS and CWS terms, right? So what you have to do for that? So you already have an expression for CWS, you will have to plug in into this. For CTBAS, what you will be doing is that again there is a desorption reaction, right? That also is going to be fast and it is going to be in equilibrium and you are going to equate it to 0, right? So from there you get the concentration of TBAS and you can substitute in that, and here again you have to make the mass balance of the total active sites and you have to re-express it for the concentration of vacant site. Correct? Hello? Are you all there?
Yes, ma'am.
Yeah. So you're able to follow, right? And then
Yes, ma'am.
now your adsorption is the rate controlling. So you just change, plug in all the unknown terms in the rate expression of the adsorption, and you will get into a final rate law of this type, right? So your final rate law will have this kind of an expression. Did you note that both this rate law derived for adsorption rate limiting and reaction rate limiting are having huge difference? You have a square term of a concentration of the vacant sites, right? When the reaction is rate limiting.
Yes, ma'am.
Yeah. And the expression completely changes. This shows something of a second order kind of thing. Whereas here you have the rate expression completely different. There are no square terms in this. So for the same reaction, you could understand that when the rate limiting step is different, then your entire reaction mechanism and your rate law expression is completely different, right? So it is very critical to identify which is going to be your rate limiting step. So if you're not getting into the right expression, then you may not really understand the mechanism of that particular reaction. So it is always important to validate also your rate expression. Okay.
Okay, ma'am.
Now we have a Elie-Riedel kinetics with surface reaction controlling. So, do you remember what is Elie-Riedel kinetics that I discussed when I was discussing the? In fact, we have there was a discussion in practice assignment problem 2 also. What happens in Elie-Riedel Riedel kinetics? You would have seen it, right? Did you follow that question? What happens in Elie-Riedel kinetics? Question number 2, and find out from this set of rate equations also. Sorry, from this set of reaction. Sorry, from the set of equation expressions also. What happens in Elie-Riedel kinetics? Are you able to find a difference between the previous set of expressions and this expression? This set of mechanisms? What is the difference?
Ma'am, in that first then there are four steps are there, ma'am. In these three steps are there available.
Okay, 3 steps are there. Which step is not there that led to this 3-step mechanism?
Absorption of water to vacant site. Ma'am.
Yes. So in Elie-Riedel mechanism, what happens is that only one of the species, one or if there are multiple species of reactants, not all species might get adsorbed. So one or more of species might react directly from the fluid phase. Mostly, for example, from gas phase. So in this case here, the water directly reacts from the gas phase with isobutene, which has been adsorbed. Okay, that is why that 4-step process has been changed to a 3-step process. Right? Are you all able to realize that there is a difference between both the mechanisms?
Yes, ma'am.
Yeah. There, in the first set of mechanisms, it was dual side with dual adsorbed species. Whereas here, Both the species are not adsorbed. One of them is directly reacting from the gas phase, right? Okay. So now again, surface reaction is controlling. So here the surface reaction is water in the gaseous phase is reacting with the adsorbed isobutene to form TBA, that is in the adsorbed phase in the active site. Okay, and then TBA then desorbs from the active site. Okay, so similar rate expressions you will have. Alright, your isobutene adsorption rate expression will be very similar to the previous case. And your TBA rate expression will also be very similar to the previous case, right? Whereas,
Yes, ma'am.
and again here, your total active sites will be a summation of vacant site plus your sites occupied by isobutene, sites occupied by TBA only. There is no site occupied by water, so this will also only have three terms in this. And then on rearranging you will get what is the vacant site concentration. Okay, so now what happens when your surface reaction is rate controlling? Here again what you will do is that you will plug in all the unknown terms or the intermediates and all, and once you plug in you will end up with the rate expression. Okay, and then since you have multiple constant terms, what you do is that you just convert it into a single one or more single simple terms, so that your rate expression looks much more in a compressed form, right? That is what I have done in the last two steps. I have taken this equilibrium constant of TBA, and then equilibrium constant of your adsorption equilibrium constant of TBA, adsorption equilibrium constant of isobutene, and then reaction rate constant and all as single term as 1 by Kp, and I have just plugged that into the main expression. Okay.
Okay, ma'am.
Yeah. Now next, uh, in this case, isobutene and water are adsorbed in different catalysts, and TBA is not on the surface, and surface reaction rate is the rate limiting. So what will be the set of reactions for this? Can someone say what might be the possible set of steps for this? I am again reading. Isobutene and water are adsorbed on different catalyst. So what will be? Any guesses? Anyone?
Well, isobutene reacts with catalyst 1 and water reacts with catalyst 2, and then the both with catalyst sites react with TBA.
Yes. So what will be the expression? Say for example, I say that the catalyst 1 is S1, catalyst 2 is S2. Okay, so what will be the first expression for isobutene? You can also type in the chat box and say someone wants to make an attempt. Okay, anyway, I'll just show you. So as one of you said, so isobutene on catalyst 1. So I and catalyst 1 we can take it as 1, S1, the vacant site in catalyst 1 as S1, and then so that will be IS1, and then water on catalyst 2, so WS2 will be formed, and then this IS1 plus WS2 will form only TBA, because TBA is not attached to any of the is not adsorbed to any of the catalyst surface, and you will get both the uh, you know catalyst surface getting freed up. That is, you will have S1 and S2 in the third step. Okay, so this again mechanism will have only 3 steps, because both the vacant sites are sites of the catalyst are released. Okay, and your expression again will be very similar to the previous set of expressions. Only thing is that you will have another subscript of 1 to denote that it is on catalyst 1 for the case of isobutene, and for 2 with the subscript 2 for water. And then what happens for the uh, mass balance for the active sites? So will it be like CT plus CV1 plus CT is equal to CV1 plus CV2 plus CIS1 plus CWS2, or how will it be? Will it be just a single total active site concentration, or it will be 2 total active site concentrations?
Single concentration, ma'am.
You're saying that it will be only CT.
Yes, ma'am.
Do you all agree, or someone else is having some other thought process? None of you have any other contradicting thoughts or similar thoughts as one of you said, is it? Actually, it will be CT1 and CT2, because it is two different catalysts. Say for example, you can have a nickel catalyst and a platinum catalyst. So your isobutene gets adsorbed to nickel, and water gets adsorbed to platinum. I am saying for example. So the total number of sites in each will be different, and you can't say it as totally CT. So it should be a separate expression for active sites in nickel, and a separate expression for active site in your platinum. That is what I have done here. Okay, and then derived what is the expression for CV1 and CV2. Finally, the surface reaction step. The surface reaction step will have your the intermediates in the forward reaction, and your concentration of TBA directly with vacant site concentration active catalyst 1 free vacant site, and concentration of catalyst 2 free vacant site in the reverse reaction. Okay, and then you plug in all these terms, and you will finally find out what is the rate expression. So you you could realize that how the rate expression changes when the mechanism changes, right? For the same two reactants, it is just the same isobutene and water, whereas we saw 4 different cases. One was where both the species gets adsorbed. Okay, the catalyst is same, but both the species gets adsorbed in 2 different sites, right? And the reaction is rate controlling. In the second case, we saw when the adsorption of one of the components is rate controlling, and in the third case we saw that one of the reactant doesn't get adsorbed at all, and it directly reacts from the fluid phase itself. And in the fourth case we saw two different catalysts, and the two reactants getting adsorbed on two different catalysts, and also the product is not adsorbed at all. So the rate expression completely changes in all these cases. So this mechanism is dual site, dual catalyst mechanism. Okay, of LH mechanism. Fine. Are you all able to follow?
Yes, ma'am.
You're getting some idea, right? For the same set of reactions, different mechanisms based on your rate limiting step, and then no sorry, different rate laws are obtained based on rate limiting step as such, and then when the mechanism changes based on the adsorption of the species also, right? Next question: the formation of propanol on a catalytic surface is believed to proceed by following mechanism. Okay, so O2 plus 2S gives 2OS. Here S again denotes the active site of the catalyst, and then C3H6 plus OS gives your propanol adsorbed on the active site, and then the desorption of your propanol from the active site. So these are the three. Now derive the rate law with surface reaction as rate limiting. So what will be the rate law? First of all, you could observe few things in this reaction. What are those? Did you find any difference from previously discussed mechanisms with this to this mechanism? Did any of you note? You could actually note in the first step itself, right? Here O2 is is getting dissociated and it is getting adsorbed on two active sites, right? I was discussing on two mechanisms, right? One is the non-dissociated mechanism and the other one is the dissociated mechanism. I also cited example of a carbon monoxide, right? Did you all remember what I was discussing in the during the session?
Yes, ma'am.
Yeah, I need someone else also to respond. I think Rohit is the only person responding, I guess. Are you all there? Pavani, are you there?
Yes, ma'am.
You are able to follow, you are able to find the difference. Here, what is happening in this case? The oxygen is getting dissociated and it is getting adsorbed in two active sites. That is why it is 2OS in the first step. You are able to, identify that? Are you all able to identify that? Okay, I am not getting any response. I'm hoping that you are able to identify that. Okay, so it is actually dissociated adsorption that is being observed. And one more difference, if you could see, this reaction is a irreversible reaction. The surface reaction is a irreversible step. Are you all noting it? It is just a
Yes,
single
ma'am.
side arrow. So in this case, we assume the pseudo steady state. That is the intermediate concentrations. The intermediate steps. Okay. We are equating it to 0. Okay. That is the intermediates are in equilibrium. Okay. And then it is the same sequence of equation you will get, right? Like adsorption step, you will have your oxygen related on the partial pressure of oxygen with the square of your vacant site concentration minus square of your adsorbed oxygen by the adsorption equilibrium constant, right? And then the reaction step will have only the forward reaction, as it is a irreversible reaction, right? And are you all able to get it? The reaction step is having only the forward reaction concentration terms. You have the partial pressure of your component B, that is nothing but your propene, and then your concentration of adsorbed oxygen, right? And then you have your desorption step, which is again a reversible step. So you will have your adsorbed species concentration in the expression, as well as your the dissociated the desorbed species concentration terms also, and the vacant site concentration. And then since it is a surface reaction control, the other two reactions you're equating it to zero, or your concentration of intermediates to zero, and then you find out what is the concentration of the intermediates, and then plug it into the final rate expression, and you get the rate expression of this. Fine. Are you all able to get some insights? You saw different mechanisms by which these adsorption is happening, and different steps that can be rate controlling, right? You are able to follow, right?
Yes, ma'am.
Yeah, okay. I think this is the end of the session. So just try to solve your assignment questions. If any doubts you get based on this, just you can ask either in the next session, or you can also post it in the forum. Okay.
Okay,
uh,
ma'am.
I think this is the end of the session. So you want any other things to be added, or uh, modified in the session pattern? Of course, in the following sessions, you will have much more, problems, numericals you might be having. Now you derive more of the late expressions. But in the following sessions, you will have a mix of conceptual questions. Like I asked you, the first two questions were all based on concepts. You will have more of a conceptual questions. You will have some rate expression derivation also, and then you will have some numericals also. Okay, and I request you all to be much more interactive, and we'll also try to solve some gate questions as well. Okay, so please be interactive, go through the session lectures, okay, the week lectures, so that you will get to have some idea, and you'll be able to discuss better in the interactive session. Okay, just feel free to interact also, because there is nothing right and wrong. If you're going to say something wrong also, no, you're going to get it corrected. Okay, so don't worry at all. It's a learning process for you as well as for me. Okay?
Okay, ma'am.
Yeah. So thank you all. So hoping to meet you all in the next session as well.
Bye, ma'am.
Bye.
Thank you, ma'am. Bye, ma'am.
Bye. Thank you.
Thank you, ma'am.
Thank
Thank you,
you.
ma'am.
you,
Thank
ma'am.
you. Thank you.
Thank you, ma'am.
Thank you all.